So we'll go ahead and move on to our first speaker, which is going to be Carle Pieters, speaking on Lunar Sample 61016, documents a rapid development of weathering products in the lunar environment.
Okay, let's see. I should be able to get this going right away. Okay, that look right?
Yep, looks good.
Okay, okay. This is a lunar sample from Apollo 16 that I'm going to be using to talk about space weathering and how quickly it appears to be performing. Okay, and sort of the bottom line will be that return lunar samples are very important to provide some of the key constraints for this very complicated assessment that is ongoing. Okay, 61016 was collected Apollo 16 by Charlie Duke. There you see him picking it up. It's probably the largest lunar sample collected. It's huge, 11.7 kilograms. It's often called Big Mooly after Bill Muehlberger, who was the leader of the Apollo 16 field geology team. Now, when it has been analyzed, this is a cut section through it. It's a very aluminous impact breccia, the bulk of it, but capped onto this aluminum breccia is a highly shocked anorthosite. And between the anorthosite and the breccias, there's a very vitreous material, very vitreous layer. The sample has been dated, and it's believed to have been emplaced at the Apollo 16 site from South Ray Crater, which is dated at about 2 million years. Okay, now I'm going to switch to how the tools I use to analyze this lovely rock. I'll be doing spectroscopy and in particular emphasizing plagioclase and anorthosites. So a couple of quick lessons on spectroscopy. Over on the left are a series of lunar samples, anorthosites that have been returned. They all have this characteristic 1.25 micron absorption, which is due to a little bit of iron in the crystal structure of plagioclase. In the bulk anorthosites, there's a few other little things depending on trace components in the sample. But if you look on the right, these are some pure minerals, a pure plagioclase, as well as an olivine and a couple of pyroxenes. And the key piece of information you need to recognize is that plagioclase is very distinctive in its diagnostic absorptions compared to the more mafic, more iron and magnesium rich minerals. Okay, now, of course, we've been looking across the moon for the characteristics of anorthosites. And it wasn't until spectrometers were flown to the moon and could look at high resolution outcrops that we were able to detect this diagnostic 1.25 absorption band. This was first found by the Kaguya instrument in 2008, followed by an overall survey in 2009, which was about the same time that M-Cube started seeing the same thing, and a highly diagnostic characteristic absorption that clearly identifies the presence of crystalline anorthosite. At the same time, however, and this goes back to longer periods using telescopic measurements, these outcrops of anorthosite are always linked to what we call featureless plagioclase. Namely, they're very bright, they're still fresh, but they have no absorptions, no crystalline plagioclase and no mafic minerals as well. So featureless plagioclase and plagioclase sort of go together. The diagnostic properties of the 1.25 micron band is key for making sure you know which mineral you're looking at. Another survey was done later using M-Cube data by Carrie Donaldson-Hanna, and all the little red dots across the moon show you where crystalline anorthosite has been identified. If you can look closely, you can see a lot of little black dots, and those are areas where the featureless plagioclase has been identified. And one of the primary hypotheses was that, well, featureless plagioclase must be plagioclase that have lost its crystal structure and therefore cannot have the electronic transitions that you have diagnostic of crystalline. So it's always thought, well, it must be some process or shocked or some form of plagioclase. Well, we do have shocked plagioclase in our collection. Here's a lovely lunar meteorite. That's a gabbro with nice large crystals, and you can see the transmitted light, and you can identify all those bright areas are the what used to be plagioclase, but now under crust polars is glass. There's no cross polar signal. So that's characteristics of glass, which has without the crystal structure. Now, what do the spectra look like? Well, unfortunately, the reality is that mescalinite, this shocked plagioclase, has a strong feature at 1 micron, which means that the little bit of iron that's remaining in the structure is slightly ordered in a wonky octahedral site. When we look at other lunar glasses, like the wonderful pyroclastic glasses or synthetic glasses made from feldspathic material, we see the same feature at 1 micron. So shocked plagioclase is not featureless. This we can also see in laboratory experiments that Fred Hertz and Jeff Johnson did many years ago with a terrestrial anorthosite, but going from a crystalline plagioclase up through higher shock pressures, and eventually you have glass. So you don't have featureless material. Shocked plagioclase, in fact, has a weak glass band near 1 micron. Okay, well, let's get back to 61016. And we had been looking for many years now, trying to understand the properties of crystalline plagioclase and shocked plagioclase. We've obtained samples that have been described as having heavily shocked. And here's some of the first 3 that we looked at. And the first 2, which are actually shown in the orange and green spectrum, have lovely crystalline plagioclase features. Oz has looked at these with particulate samples, and yes, indeed, it's largely crystalline plagioclase with only minor amounts of mescalinite. Well, we had one sample, our first sample of 61016 that we looked at. We said, oh my gosh, it's flat. There's nothing there. Maybe we found it. Well, but if you look at that, that doesn't look quite right. It shouldn't look like that. A, it's too dark, and it's really, really featureless. And it turned out, yes, that sample, which was saw fines, had some contamination in it from the saw, and that was wiping out the features. So the curatorial group were very kind to prepare us 2 new samples of the same rock, specifically to meet the requirements that we're trying to look at, namely this shocked component.
2 minutes left.
Okay, and I'm close. These are the 2 samples, one that has a chip of that anorthosite zone and the vitreous material below it. And here's a first sample of the vitreous material, large grains. Because they're large grains, it's relatively dark. But if you expand the scale, essentially what you see is a lot of mescalinite, the glass, and a little bit of anorthosite. And this is held up by the analyses that Oz was able to look at as well. So completely consistent story, but it's not featureless. Well, when we look at the chip, here we have this very, very shocked plagioclase, as well as this part of the plagioclase that was exposed to the surface since emplacement Apollo 16. When we look at that, this is what we get. And the first thing I'm going to talk about is in both of the shocked plagioclase as well as the patina at top, you can see the effects of the mescalinite, the clear glass bands. But what you can also see is that the exposed surface clearly has some weathering components. And the classic characteristics of nanophase iron. So there's no question that this exposed surface has undergone in only the 2 million years that this rock has been exposed at Apollo 16 to accumulate weathering products that we all know and love. So the summary, the main conclusion is that this big Mully shocked anorthosite, emplaced from South Ray Crater, dated about 2 million years, exhibits clear weathered surface patina that must have developed within the last 2 million years. And it's probably less than that. For those of you who know the environment, there's micrometeorites that will abrade the surface constantly. So that's an upper limit of the time scale. The second thing that is likely is that the source of the nanophase iron is not likely to be the anorthosite itself, in that you need to mobilize the iron atoms so that you can have them collected into these individual nanophase components. So you need some mechanism of redistributing any kind of FeO across the sample. And it's unlikely to be the anorthosite itself, which requires some remobilization, perhaps by micrometeorites. There you have the basic story. I don't have time to go through the others, but there are other obvious conclusions that have to do with the character of anorthosite and the featureless plagioclase, which we still don't understand. Last comment I'd like to make is that obviously the lunar samples, and we've looked hard, we haven't examined them all, of course, but the lunar samples continue to provide remarkable discoveries, even though their scope is limited. Clearly, we would love to have additional anorthositic samples, especially those that are probably very friable and are going to be hard to collect. That may be giving us clues where our featureless plagioclase is associated with. So let's get more samples. Thank you very much.
Thanks, Carly. We'll just do one quick question. We have one in the chat window here. Do you expect to see widespread shocked plagioclase on the lunar surface, and where do you think they're most concentrated?
That's the $64,000 question, as we used to say. We don't know. Clearly, there is shocked plagioclase. Clearly, it is distributed. We see mescalinite in the laboratory, but we don't see mescalinite in the remote measurements. We see crystalline in the laboratory, and we see crystalline in the remote measurements, but in the remote measurements, we see featureless plagioclase. How is that discrepancy resolved? I don't know the answer yet. There are several hypotheses that might work, but we don't have a definitive answer.
All right, great. Thanks again, Carly.